This is video 41 on MicroPython and LVGL 9.3 on a Pico USB board. A nice ST7796 display at our favorite online retailer has a different touch interface. The LVGL MicroPython GitHub site has the SPI-based XBT2046 driver and the I2C-based FT6X36 driver. In this video, we look at the I2C driver. Please let us know in the comments if you like this example, or let us know if you have suggestions to improve it. For this effort, our test rig uses a standard RPI Pico USB board with an affordable 4.0-inch ST7796S display. As this channel covers multiple small system solutions over time, please subscribe to stay informed, and click like, as that really does help. Our goal for this effort is to add the Capacitive Touch interface and discuss a few details pertinent to controllers used by Hosyond. We shall discuss the generic FT6X36 driver available at the GitHub site. We'll discuss the Hosyond display and its CTP Touch module. We'll present the Hosyond CTP interface in the physical pinout. We'll demonstrate the driver using our standard programs. Finally, we'll discuss the touch driver and the display driver code. The program files are at the GitHub site that is mentioned in the description and endnotes for this video. The generic I2C driver from the MicroPython LVGL binding GitHub site is based on the FT6X36 touch driver. The author sets the hex address 0x38 for the controller, but expects us to provide the I2C pins and the display dimensions. Earlier in this research, we validated the hex address using our test scan I2C program. The generic driver defines an indef with a callback. Since LVGL controls an indef, the callback is executed constantly. So it is constantly pulling the controller for 11 bytes at register 2. The driver defines a variable called presses from the first byte returned. The author coded for 1 or 2 touch values. However, LVGL can only manage single touch values. Nevertheless, the touch values are converted and transformed by the swap inverse flags and then stored in the data point. Finally, since a touch occurred, the data state is set to indef state pressed. And an important takeaway is that the variable presses is constantly updated with the touch count. Also, the author intends to handle screen orientation using the swap inverse flags, which we will see more later. For testing, the Hosyond MSP4031 display was purchased. The display is type ST7796S with 320 by 480 pixels. This display uses the I2C FT6336 touch controller. The display contains 2 extra pins though, a CTP reset and a CTP INT. Let's pull the datasheet. From the Hosyond website, we found a datasheet which diagrams the host interface. Interestingly, it depicts the reset and interrupt signals. It turns out that the CTP reset line must be pulsed low to wake up the touch controller. Thereafter, any touch triggers low the CTP interrupt line. Now we can read the controller and get the touch points. By the way, the presses variable always returned to 0. This slide presents the various Pico pins we associated with the display and touch pins. Here is a picture of the wired test rig. We continue to use the April firmware in our Pico USB board. We use our standard driver files. We include the modified touch driver, which is renamed as CTP FT6X36.py, and we updated the display driver file. So you can just grab the files from the GitHub site. Now that we have an idea of the approach, let's see what actually happens. We open the demonstration program files in Thony. Here, let's look at the first demonstration, which is test-button3 display.py. We've already clicked the green run icon to execute. Wow, even at 3.3 volts, this display is bright and easily viewable at many angles. This is the single button program. It's a good first-time program because the button is large and centered, making it easy for even non-calibrated touches to work. It turns out that the Hosyond display returns calibrated values. So when we touch the button, a message appears in the Thony shell. Let's touch the button. And let's touch it again. Alright, you can see the messages appear in the Thony shell. Let's look at the second demonstration program. And we'll restart the program. This program is a matrix of buttons. It is being displayed in portrait mode. It's useful to verify that you have managed the orientation and calibration properly. There are many buttons across the screen. Touching one reveals the name in the Thony shell. Let's touch a couple buttons. All right, 60.4, 160.9, 210, 10.1, 260.9, 10.9. Okay, the touch works very well. And this demonstrates the display and driver very well. Now let's look at the third example, which is test_keyboard3_display. Let's stop the program and we'll restart the program. All right, you can see the keyboard is in portrait mode. Let's stop the program again and put the keyboard in landscape mode. Okay, we'll restart the program. This program displays the keyboard, a text area box, and a button labeled clear. It's useful to verify that your calibration is very accurate. There are many buttons across the screen. Touching them places that letter in the text area. All right, we put the word dog in the text box. Let's press the clear button. All right, these three programs demonstrate the display and that the touch driver work very well. So now let's look at the code. We've opened the program to CTP_FT6x36.py. The MicroPython code is modeled on the generic FT6x36 driver. However, I had to make changes. Beginning at line 29, we added the CTP and reset buttons. You can see that we pulsed the reset to wake up the CTP module. Now let's scroll down a little bit further. You can see here at line 54 that we defined an interrupt trigger for the CTP line, and it calls fetch. If we look at this code on line 49, we can see that it does one thing, which is to set the touched flag to 0, and then it sleeps for 20 milliseconds. And that's just so we can debounce any touches. And that's it. Now, based on the indef that we defined earlier, we're going to let LVGL call this callback. Let's take a look at the callback. In line 86, within the callback, it checks to see if the previously saved touched value is 0. If it is, then it updates the data point with the getPoint function, resets the touch flag back to 1, sets the data state to indev state pressed, or if it wasn't touched, it sets the state to released. Let's take a look at the getPoint function. In the getPoint function, it calls the getTouch value, which we'll look at in a minute. It then proceeds with the touched values and transforms them based on the swap and inverse flags that were set by the display driver that you'll see in a few minutes. Let's take a look at the touched value function. The touch value function is going to read at address 3 10 bytes. It's going to take those values and convert them into X and Y values and then store them in an LVGL point variable. It returns that so that the getPoint function can process the touch values. All right, that's pretty simple. Let's take a look at the display driver changes. Okay, the first thing we see is in line 15, we have replaced the XBT 2046 SPI base driver with the I2C driver, which is CTP_FT6X36. In this case, it's going to import the FT6X36 class because I kept the same class name. Now, an important thing is that I've created this use CTP driver flag so that we can skip large sections of code. For example, since we're using the I2C driver, we don't need the SPI driver that we normally would create for the touch SPI device. Here at line 52, we're defining the display as an ST7796, and you can see that we've set it in landscape mode. All right. Again, we're going to skip over the XBT 2046 driver. And because it's true, we're going to use this set of statements to define the display touch driver. Now, notice here that we've got, let me scroll a little bit. We have the touch being defined at different display rotations. So here we've set the inverse X and Y and swap values either to true and false, depending on their needs in that orientation. And that's a feature we discovered that the original generic FT6X36 driver did. So we kept that concept here, and I like it a lot. It allows us to skip a lot of code. All right, so based on this, you can see that the orientation is being defined in the display driver, but it's being actually performed in the CTP_FT6X driver. All right, now we skip a huge section of code because all this transformation is needed for the XBT 2046. But we don't need it because the calibration is already performed for us within the module, and the orientation is handled as we saw above. Finally, we come to the InDev. Here we have the InDev device for our screen, but we skip the callback since LVGL can use the CTP driver's callback. So notice we're skipping this section right here, and we're using the callback that we discussed earlier. So the display driver file is now greatly simplified by using the CTP FT6X36 driver. In summary, in this video, we discuss the generic FT6X36 driver. We discussed the specific details about the Hosyond CTP module. We demonstrated 3 example programs which helped us to verify the XY transformations. We reviewed the CTP FT6X36 driver and the changes we made to the display driver file. Hopefully, you'll learn more about the I2C Touch interface and found a new display. This driver file was only tested on the Pico, but it should work as well for the ESP32 platform boards. Please comment if you feel other changes are needed. I hope this video helps your LVGL MicroPython coding. Thank you for listening.